All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good.
Good to hear. All right, and so the plan for today is I do want to talk about the project, the midterm project, okay? I posted this last week, but we didn't get a chance to talk about it just because we had the ANSYS activity. And so I want to make sure I go over it just so we're all on the same page of what I expect from you and what the steps you are that you need to do to complete it. Okay. And so that might take maybe 15-20 minutes of class, and then from there we're going to start launching into our next set of lecture notes. Okay. And so the theme for today and for the next few weeks is going to be all on meshing stuff, right? And so I've been telling you guys that we're going to spend a lot of time talking about meshing, just because there's a lot of nuance and there's a lot of knowledge that that there is to meshing. And so we're going to go pretty deep into all the element types. You guys know the basic ones at this point, but beginning of next week we're going to talk about shell and beam elements, which are pretty important. And then after that, we're going to start talking about more advanced meshing. Okay. And so, meshing is going to be the theme for the next few weeks. All right. So before I get to that, I don't think I have any more announcements. Activity 3 is due this Friday. And so just as standard for the ANSYS activities. Okay. So besides that, are there any questions I can answer before we get started? Okay, all right, so let's talk about the project. Okay, and so I'm on Canvas right now. And so if you go to Canvas, you can find all of the project information from here, okay? And so if you go to our course website, you can go to assignments. And if you look under midterm project, you can see that there's only one option there, and that's for this, okay? And so what I'm gonna be reading for you guys is the instructions first, okay? But I also have the rubric, and I also have a template that you can use for the report, and also the CAD files for these, of course, as well. Okay. All right. And so the basic idea with the midterm project is to basically put together everything that you've learned up in ANSYS up till this point, and then kind of put it all together into a single analysis. Okay. Because up to this point, we've been doing all the activities. And through the activities, we've been introduced to a lot of the basic features in ANSYS. Okay, so how to perform a 2D simulation, how to do a 3D simulation, how to do one with assemblies, how to mesh, apply boundary conditions. We've kind of walked through all of that so far, in our 3 activities. Okay, and so at this point in the class, I think you guys are ready to put it together and to do a finite element analysis front to back. Okay. And so the idea with this project is to kind of, put you in the shoes of like a professional engineer where, you've been given a CAD file from either your team or your manager, your company, and you need to put together the analysis for this, for this. Okay. All right. And so I'm giving you some options. And so there are 2, you'll notice that there are 2 geometries here that I've given you. Okay. And so one is for this shaft housing here, right? And so we have this this kind of cylindrical shaft that's kind of the main piece of this part, and then there's some attachments to it, and then it's fixed in place by these bearings on the right side, okay? And so that's one of the projects, and then the other possible geometry that you can have is a globe valve, okay? So this is the CAD geometry of a globe valve, okay? And so you don't have to do both. And you don't get any extra credit for doing both. And so, just pick one, just pick the one that you feel most strongly about, that you feel that, you can do a good analysis on, and then focus just on that one. Okay. But please don't do both, because it's going to be a lot of work otherwise. Okay. And so in terms of, what I think of both of these geometries, I selected these 2 kind of on purpose for this class, because, this is a graduate level class. And so these CAD models are fairly challenging, okay? And I will say that these geometries, they have been designed for finite elements, because I took them from previous activities that I've had from other classes as well. Okay, so they are doable. It's just that there's a lot more work that you have to do for these geometries, relative to the geometries that I've been giving you for the activities. Okay, and so most notably, what I want you guys to focus on, and I think it's more obvious here for the shaft housing versus the globe valve, is that there's a lot of extra parts to this geometry, right? And so you can see that in this CAD model, they've CAD'd up all the little nuts and bolts, all the little, all the little, fittings here, okay? And so, one thing I really want you guys to think about when you're starting to do this analysis is what is the most important parts of this geometry in terms of its structural strength, okay? Because, what you're going to get from this finite elements is you're going to get values for the deformation, you're going to get values for the structural stress, okay? And so I want you to think about, what are the main load-bearing devices or load-bearing parts of these assemblies? And I want you to focus just on those, okay? Because I'll tell you right now that if you try to take these geometries and you just try to mesh them right out the box and run a simulation, you're going to run into a lot of challenges because there's a lot of parts of these assemblies, and most of these parts I would say are not necessary to do a finite elements. And so, think about, what are the load-bearing structures, and then just focus on that, and then, and make liberal use of the suppress feature, because you're going to need to suppress a lot of parts in these assemblies in order to get a decent mesh and a decent simulation off, okay? And so think about that as you're doing that. So both geometries do have a lot of superfluous parts. I'd say more so on the shaft housing than the globe valve. The globe valve doesn't have as many parts, but you do still need to suppress quite a bit here, okay? All right. And so one thing that you'll find probably useful, especially if you do the globe valve, is that you might be interested in applying a boundary condition on the interior of the pipe. And so you might have to make use of this feature called hide faces, okay? I think maybe I'll hold off on demoing that in the class until later, just because I think there's a better geometry for me to demo it on. But just be aware that if you're doing the globe valve, applying boundary conditions on the inner face of the piping is going to be a big part of that as well. Okay, so that's one thing to keep in mind. Okay, and the kind of the organization that provided these CAD files is called the ANSYS Learning Hub, and so they kind of get the credit from this. Okay, but I did do simulations on these, so I know that they're doable, and so I think they make fine subjects for this project. Okay. Okay. So any questions so far on just the idea behind the project and the CAD files? Okay. Right. Okay, so let's talk about requirements. Okay, and so your project, I mean, of course, a big part of your project is going to be running the finite element simulation. Okay, but I would say the bigger part of this project is actually formulating it into a scientific report. Okay, and the report is actually what I'm going to grade you on. Okay, and so your report needs to have a lot of different components in here. Okay, and so the first requirement that I'd say that your report has to have is some kind of objective. Okay. And so the objective, the way you can think of the objective is, you need to ask yourself, what am I getting out of this finite elements simulation, or what kind of information that am I looking for? Okay. And so far in the class, we've done 3 activities of structural finite elements, and we've seen that, we can simulate things and predict things like what's the deformation going to look like, what's the stress going to look like, what's the strain going to look like, right? And so for your part, I want you to come up with kind of a backstory behind it, right? And so think about, why would someone want to do a finite element simulation on this particular part? What kind of loading are we, is kind of expected in a part like this, okay? And so you're going to have to do a little bit of research too about, what are some common applications for a shaft housing? What are some common applications for a globe valve, right? And, think about, a lot of times you're doing a finite element simulation to predict whether a part like this is going to fail, if it's going to break, okay? And so I want you to think about, what is a common way for a shaft housing like this to break, or a globe valve like this to fail, okay? And then work that into your objective, okay? And so your objective should be, we're looking specifically, whether the shaft housing is going to fail under this particular loading scenario, okay? Right. And the reason I'm having you really think about this is that, a finite element analysis is never done in a vacuum, right? And so what I mean by that is that, you never ever just get credit for completing a finite element simulation, right? And so, you run a simulation, you produce a pretty plot, no one's going to congratulate you or thank you for your work, right? And so most of the time, they want to find out something, something of practical significance about this part that, and that's the reason you're doing the finite elements, okay? And so I'm leaving this up to you, you know, on kind of on purpose, you know, just to kind of, I want you to kind of get thinking about, you know, if there's a part like this and someone is requesting a finite element simulation for it, you know, what would they be interested in? Okay. And this is going to form kind of the backbone of your report, okay? Because your project objective or your finite element objective is very much like a hypothesis, right? And so if you think back to a lot of the lab classes you've taken, or if you know if you've done any experiments for, you know, for an internship or something, you know, whenever you do an experiment, you know, those are never done for you know, for fun either, right? A lot of times you have some kind of question or some kind of hypothesis that you're testing, right? And so finite elements is the exact same way, right? And so I want you to think about, you know, what's your hypothesis going into this finite element simulation, and, you know, how are you going to use the simulation results to answer that objective or to answer that question or answer that hypothesis, okay? Right, and so I gave you some example questions that you might consider, okay? And so you don't have to answer all of these questions or make all of them part of your objective, but, you know, I want you to kind of come up with a reason, come up with an objective of why you're running this simulation, okay? And so some questions might be like, you know, are you interested in the mechanical stress, right? Are you interested in failure or failure simulation, right? Are you interested in deformation? Okay. Are you interested, or maybe you're interested in minimizing the cost of production, right? And so, you know, one way that you can spin this this project is, you know, we know that this geometry might be under some certain forces, but maybe we've over-designed the part. Maybe we've put in too much material in there, right? And we can actually manufacture this part at a lower cost, okay? And you can use your simulation results to back up that that claim, okay? And so that's another possible angle that you can take, okay? Or maybe, you know, or maybe you're designing a new part and you're using this as part of the design criteria, okay? And so, you know, think about it, right? And so, you know, there's no right answer to this, and so there's a lot of different ways that you can take this analysis. And so I've kind of left it open kind of on purpose, just so that, you know, you can kind of take it in whatever creative way that you want. But you do have to have a goal, okay? And so you can kind of, you know, the way I think of it is that you can take this project wherever you want, but you need to know where you're going, okay? So you can't just do random simulations and let that be it, okay? All right, any questions on the project objective or finite element objectives? Okay. All right. And so I'd say the next most important point is your methodology, okay? And so in doing your project, you're going to have to make a lot of decisions on your finite elements, right? And so some questions you have to answer is, you know, what kind of material are you going to use, okay? What are the properties of this material? What kinds of elements are you going to use? What is the element order, okay? How many elements are you going to use? And are you applying any refinements in any certain areas? Okay? What kinds of loads and what kinds of constraints are you applying, right? And so, you know, these are all questions that you have to answer as you set up your finite element simulation, okay? And I want you to be very detailed on, you know, first of all, listing out what you did, okay? Because that's an important part to, you know, any finite element simulation, is being clear about all the settings and all the parameters that you chose. But more importantly, I want you to be able to justify your decisions, okay? And so if you chose a hexahedral mesh, or you chose a quadratic element order, you know, I want you to be able to explain why you're doing that, okay? Because this is something that's really important for the professional engineer, okay? Because what you'll learn, you know, if you get out into the real world and do finite elements, what you'll learn very quickly is that no one is going to believe what you did was legit. And I talk a lot from experience myself, you know, and you know, a lot of my experience is from the research world, but you know, I've had friends that tell me a lot from industry as well. And so in order to get people to believe what you're doing in finite elements is actually good, right? Because I'll tell you the impression that everyone's going to have. So if you're a young engineer coming into a company and you're doing finite elements, everyone is just going to think that, oh, he or she just you know, just punched in a bunch of buttons and he made some pretty pictures in ANSYS, and then, you know, and then that's it. And so, you know, it's up to you. It's up to you to kind of convince people and prove to them that, you know, there is you know, a methodology to, you know, what you chose, and there's a reason why you chose everything, and that's to get the most accurate result possible, right? And so, you know, you need to be able to justify your decisions about, you know, why you meshed a certain way, why you apply the boundary conditions in a certain way, okay? And because it's that justification that's going to be important, when you present your finite element work to a supervisor or to a team or to anyone. Okay. And so I want you to think, as you're going about your finite elements, in every setting and every click that you do, I want you guys to think about, why am I doing this and how can I justify this to someone who might be skeptical of my work. Okay. All right. And so this next paragraph says that, a significant portion of your grade will be determined based on how you chose to do the meshing, the boundary conditions, and the material properties. Okay. And so, I expect to see a lot of subsections in your report that explain what you're doing. Okay. And so just like with the objective, there's no perfect way to do this stuff, right? And so I'd say there's lots of different ways you can mesh and apply boundary conditions. And so I'm not looking for one particular, there's no right answer to that I'm looking for. What I'm looking for more is that, you make these decisions and you justify to me why you're doing that. Okay. Because at this point in the class, we've learned a lot about, first of all, just of ANSYS, but also, a lot of the theory behind like meshing and boundary conditions and material properties. And of course, we're going to learn more over the next couple of weeks that you should be able to give good justifications for everything that you're doing. Okay. And so that's what I'm going to be grading you more on versus, oh, I expected the number of elements to be, 30,000 and you have 28,000. I'm not really looking for that. I'm looking more for, how do you justify these things, based on what we've learned in the class. Okay. All right. And just like the last activity, I want you to think about a few different loading scenarios. Okay. And so I don't want you to just think of one. And so, I have 3 here. But maybe I might reduce this down to 2 because these geometries are pretty specific already. And so coming up with 3 different loading scenarios might be that are pretty different from each other might be a little bit tough. But we'll see as the project goes on. Okay. But I do want to see different conditions, so maybe different material properties, maybe different boundary conditions. Okay. Like different scenarios that you can test out and ANSYS that you can that you can simulate. Okay. Okay. Any questions on this? Okay. All right. And so next you have to show your results. Okay. And so I think actually you all have gotten a lot of practice with this. And so for the results, I expect you to have screenshots of your distributions. Okay. But another thing that I want you to have is some explanation in the text. Okay. And so what I don't want for your results section is I don't want you to just put in 20 different screenshots from ANSYS with no explanation. Okay. And so, in the text, I want you to explain, here is my results for the total deformation. The maximum deformation is this, and you can see it at this location right here. Okay. And so you should explain to the reader, what they should be looking for in your pictures. Okay. Because it might be really clear for you that if you simulate something in ANSYS and you produce like a stress distribution or a deformation distribution, it might be very clear for you, what you're looking at there. But, for someone that may not be familiar with your part, or what you're doing, you might have to have that explanation. And so, make sure you give a little bit of explanation for your results. Okay. All right. And then after the results is the conclusion. And so the conclusion, you just have to kind of wrap things up and just kind of summarize your report. Okay. All right. And so at the end of this instructions here, you can see that I told you that there's a template. Okay. And so please use the template. And so you actually get a lot of points on the rubric for just using the template. It seems like a silly thing, but I can't tell you how many reports I've gotten in the past that don't label sections or they don't use the template, and I have to kind of hunt for what they're doing. And it's not a fun experience. And so please just use the template, if anything, just for the sections. Okay. If you think the font is ugly or the spacing is ugly, you can change that stuff. The main thing is I just want everything to be separated in sections. It kind of makes my life a lot easier when I'm grading. Okay. And so in terms of the length, honestly, this is the first time I'm running this project, and so I don't really know what to expect for the length. But I will say that there's no requirement, and so I don't expect a minimum and there's no maximum. But kind of just looking at the report and kind of thinking about how much work has to be done, I would think that it might be around 12 to 15 pages, especially with all the figures that I'm asking to include. But it very well could go up to 20, 25 pages as well. And so, the main thing with the length is that I tell people not to stress about it. just, what I tell people is that it's more based on the content, right? And so as long as all the content is there and you give adequate explanations for everything, then that's all that I'm going to be looking for. You don't get any more or less points for having it longer or shorter. And so, don't stress out about the length too much, but people always ask me for a ballpark of what to expect. And so, it's a bit hard just because it's the first time, but I would say 12 to 15 seems reasonable to me. But of course, you can go over or even less than that if you're good with your formatting. Okay. And I've also posted a rubric that we can look at as well. Okay. All right, teams. So there are no teams, and so this is an individual project, and so I want everyone to perform their own analysis, and of course everyone to write their own report. Okay. But with that said, feel free to collaborate with your classmates just in terms of of getting past ANSYS errors or just helping thinking up loading conditions. Okay. And so I don't mind that. And so, you can definitely feel free to work with your classmates on in that sense. But, everyone has to write their own report and expect everyone to take their own screenshots and do it in ANSYS themselves. Okay. Right. All right. So final remarks. And so, I'm going to be available to you guys for this throughout this entire project. So, don't hesitate to reach out and, and please, don't wait until the last minute. Okay. Because it's, I'm giving you a lot of headway for this. So I'm giving you over a month to do it. And so, there's kind of a reason for that, because I think it's going to be a pretty decent amount of work. And so, the earlier you start, if you think about it in terms of like, it's inevitable to kind of run into issues with the ANSYS or to run into questions when you're writing the report. And so, the sooner that you start, the sooner you can get those issues resolved, and kind of the more smoothly your process is going to go. Because I'll tell you right now that I'm telling this to you and my undergraduate finite element class. I'm telling them the same thing, to start early. But even then, I know a lot of people are going to wait to the last minute. And so if you wait until the last minute, then you're kind of getting in line behind maybe 15, 20, 30 other people that have questions as well. And so during those times, sometimes it takes me a while to get back to you in terms of answering the questions. So, the sooner that you start, the sooner you can ask your questions, and then the sooner you can get answers from me. Okay. Okay. Any questions? Any other questions on the instructions here before we look at the template and the rubric? Okay. All right. So let's look at the template really quick. So it's a Word document, and so you can just kind of edit it in here. Okay. And so you can see here that I've created all the sections that I expect. Okay. But of course, when you actually write your report, it's going to be a lot longer because it's, you're filling in the screenshots and everything like that. Okay. But here's a template that you can use. But, if you don't want to use this, if you think Times New Roman is ugly, then that's okay. I don't have any personal feelings towards Times New Roman, but that's just what I chose for this template. But, so use whatever you want. The only main thing is that please have the sections. That's the only thing that I ask. Okay. And because if you look at the rubric, the way the rubric is designed is I go basically section by section, and I make sure that that you have everything that I'm asking for there, and that it's neat and well written. Okay. And so I grade you literally section by section. And so if you can label each of the sections for me, it's going to make my life a lot easier and make me not annoyed. And so if you generally you don't want to annoy the person that's grading your work, because that's usually not a winning strategy. Okay. Funny story behind that. So I took a class in grad school from a Spanish professor, and he was very Spanish. And so this was the year that Spain lost really badly to Germany in the World Cup, like 7-1. And that happened right as we were taking our final. And so I was walking down the hallway, and I saw him, and I could tell that he was very upset because he saw the score. And so I was trying to avoid eye contact with him. But then he still singled me out because, I guess he kind of blames me for whatever reason that they lost. And so he asked me, did I see the score? And I said, oh, what score? I tried to be dumb. But then he said, yeah, Spain lost 7-1. I'm like, oh yeah, that's pretty bad. And he's like, yeah, you think that's bad? I'm gonna go grade your final right now. And so, it kind of made me scared a little bit. So, you generally don't want to do that to the people grading your stuff. Right? Okay. And so, that's all the documents here, and then the CAD files are here as well on the assignment. Okay. All right. Any final questions on the midterm project before we start the lecture for today? Okay. All right. And so, question. Let's see. Yep. Yeah. And so, it's a lot to do. I know it's a big project, but I think it'll be something good. Okay. And the nice thing about projects like this, and your final project will be kind of similar to this as well, but of course it's going to include more stuff. I think one nice side effect of this project is that you're going to have a really nice finite element report at the end of this. Okay. And you can take that report and put it in your portfolio and to show off to employers, right? Because I think it's one thing, and I've seen this with students, and I've seen this with my friends too. It's one thing to put on your resume. It's one thing to say that you know ANSYS. It's another thing to actually bring something to the interview or to show to your recruiters that hey, I did this analysis and here's the report for it. Here's the receipts, or here's to prove that I actually know how to find elements. And I've had students come up to me and said, I brought my final report with me to the interview, and it really impressed the interviewers, and they offered me a job because of that. And so I think this is a nice opportunity to get something like that. All right, so let me go ahead and share my iPad. Okay. All right. And so, unfortunately, I'm only going to flash just for a little bit, but basically the theme for this week and the theme for, all the way leading up to the next ANSYS activity is we're going to be diving a little bit deeper into the different types of elements that you can have. Okay. And so specifically, we're going to talk about, we're going to talk a lot more about element order today. Okay. And so we're going to define something called a shape function. And then we're going to use that as pretext to kind of really dive into the differences between, what's the difference between a quadrilateral and a triangle? What's the difference between a linear and a quadratic element? Okay. And so we're going to look at kind of the equations behind that, and to kind of really, to have kind of a deeper understanding of what's the difference between them. Because we went over pretty briefly when we talked about our meshing basics lecture, but it's a really important point, and it's one that kind of drives up kind of the decisions that you're going to make in terms of your meshing. Okay. All right, and so let's start by revisiting element order, and then we're going to introduce something called a shape function. And so to start, let's kind of remind ourselves, what element order means, right? And so when when people say, or when people talk about the order of an element, what they're really referring to is the polynomial order of the approximating function. Okay. Okay. Because remember the way the finite element works, right? So remember, finite elements, we're never looking for an exact solution to our differential equations. Okay. Instead, what we're looking for is an approximate solution. Okay. Right. And so remember, the way that we find approximate solutions is that we first assume a form for the solution, right? And so we basically assume that the solution is going to look like a polynomial, and then we look for the best polynomial that fits that that fits the solution. Okay. And so the two options that we have are either a linear polynomial or a quadratic one. And so, for now, I'm going to show you the 1D versions of these polynomials, but later on as we get to the 2D and eventually 3D element shapes, we'll talk about their multidimensional forms, right? But for a 1D form, a 1D linear polynomial, we just have two terms, right? Okay, and so we have our constant term a0, okay, and then a linear term a1x, okay. Whereas the quadratic form will have three terms associated with it, right? And so a0 plus a1x plus a2x squared. Okay? And so to give you kind of an analogy of how this works, it's kind of something like this. And so, I don't know if you've ever used this feature in like a spreadsheet program like Excel or Google Sheets, but a lot of times, you might give to Excel a list of data points, right? And so maybe you'll plot the data points something like this. Okay. And so for this one, I guess we have a particularly messy data set, okay? And so a plot like this is, we call this a scatter plot. Okay. Right. And so when you make a scatter plot like this, one feature that Excel has that you can use is you can apply what's called a best fit line, right? Okay. And so with the best fit line, what Excel is doing is that they look at all the data points here and say that if we try to fit a let's say a linear function, or maybe a quadratic function, or maybe an exponential function, what's the best linear function that correlates best with this data, right? And so let's do a linear function first. And so just randomly, maybe our best fit linear line might look something like that. Okay. Right. And if you're ever curious about how Excel does this, is that they use a process called least squares. And so what that basically means is that, the way they determine this line is that they measure the distance or how off all of the data points are from the line, and they find the line that has the least square distance, between the line and all of the data points, right? And so that's why they call it the best fit line, because it's the line that best fits the data. Okay.
Professor?
Yeah.
Is that also called the R-squared value?
Yeah, the R squared is related to that. So the R squared basically tells you how good a fit it was. And so the more R squared is closer to 1, then the better fit it is. Yeah. Mm-hmm. Right. And so, if you've ever played around with this feature, that, no matter what your data looks like, you can fit any curve that you want. And so you can do a linear curve, you can do a quadratic one, you can do a polynomial of any order, you can do an exponential function. I don't think they do sinusoids, but they might have that too, right? And so you can choose, whatever function that you want, regardless if that function looks good or not, or if it looks like it fits the data, you can kind of do whatever you want. Okay? And so finite elements, it doesn't exactly work like this, but the idea is similar, right? And so the idea with finite elements is that underneath your geometry and underneath your boundary conditions, there is a solution. There is an exact solution out there, right? And so that exact solution might do some really crazy stuff, and a lot of those exact solutions to PDEs can be crazy stuff, okay? And so what finite element says is that, I'm not going to waste my time to look for the exact form of that function, because that's going to be really crazy. And so instead, what they're saying is that, we're going to say that, we're going to find the best linear fit or the best quadratic fit to this finite element solution, right? And then, and we're going to roll with that. And then that's going to be our solution, okay? And so the thing that you're interested in, and the thing that finite elements actually solves for, are actually these things. Right? And so these constants right here, these are the coefficients of the polynomial, and so these are what you're actually solving for. Okay, and so if you think back to Excel, right? And so when you make this best fit line, you can actually ask Excel to put the actual mathematical form of the function. And I think it also lists the r² value when you do that as well. And so the function might be, mx plus b or something like that, right? Where m and b are some, in some cases might be some, irrational decimal number that, that's impossible to remember, okay? But in that same way, right? So when Excel finds the best fit line to your scatter plot, what they're solving for are the values for these constants, right? And so finite elements is doing kind of the exact same thing. And so they're trying to find, what are the values for these constants that best fits our the solution to our differential equation, okay? And so the difference between linear and quadratic is that it's kind of a different amount of work for both, okay? And so, kind of like what we talked about before. So for a quadratic polynomial, you're more likely to get a more accurate solution, okay? Because you have this quadratic term. But it's going to be a little bit more work, because per element you have more constants that you need to solve for. And in fact, you're going to have more shape functions to worry about too, and more nodal values. Okay? And so one of the main differences that you'll see between linear and quadratic finite elements is that quadratic finite elements will always give you more nodes than linear finite elements. Even if the number of elements is exactly the same between a linear and a quadratic mesh, the number of nodes is going to be more in the quadratic one. Okay. So any questions on this so far? Okay. All right. And so, let's talk about that point a little bit more. Okay. And so I'm going to illustrate this concept with 1D, but then you can imagine this trend continuing for for 2D and 3D as well. Okay. And so let me go ahead and write the functions again. A quick question. So is there a higher order than quadratic? There is. And so, in theory, you can have as high an order as you want. But then the question becomes how practical is it? Because the main thing that you get with quadratic is that you can start to have some kind of curvature to your solutions, right? Because for a linear function, you can only go straight in a straight line. But for a quadratic term, that's when you actually start to have some curvature in your solution, right? And then just kind of based on what people have tried in the past, that curvature aspect is kind of probably the most important thing to getting a good approximation. And so I think what people have found is that once they go higher than quadratic, and so they go cubic and fourth order, then you start to lose any kind of benefit in your solution. Right? But there are reasons why you would want to go to cubic or fourth order. And those are mostly cases when your differential equation is more challenging. Yeah, and so if your differential equation actually has, third order, fourth order, in some cases, fifth or sixth order derivatives, those are the times when you actually need to get higher than quadratic. But the nice thing about structural equations, and same thing for thermal equations, and same thing for fluids, is that the highest order derivative that you'll see in these equations is only second order. And so with that, you only need up to a quadratic function in order to get everything that you need. Yeah. Okay. And so here are our two functions for the linear and the quadratic. Okay. And again, in purple, I'm going to circle, what we need to solve for. Okay? And so the way these constants are typically solved for is that they're solved using a linear, a system of linear equations. Okay. Right. And the thing about algebra, if you think back to how algebra works, in order to solve for a certain number of constants, that tells you that you need to have the same number of equations. Okay. Okay. And so for the linear function, you can see that we need two equations, right? Because we have two constants there, right? But for the quadratic function, we need three equations because we have three constants. Okay. Right. And so how do we actually get these functions? And so the way that we get these functions is that we do them based on the number of nodes in our elements. Okay. And so that's kind of the reason why where if you have a quadratic element, those elements are going to have a lot more nodes to them because they just require a lot more equations in order to solve for the constants. Okay, and so let me show you how a linear 1D equation, how we solve for those constants are. And so for a linear 1D element, you can see that because we have two constants, we're going to have only two nodes to this element. Okay, and so we'll call this node 1, and we'll call this node 2. Okay. And so on this element, we're going to have our approximating polynomial. Okay, and it's going to have u of x is equal to a0 plus a1x. Okay. Right. And so we need two equations in order to solve for a0 and a1. Okay. Okay. And so the way that we're going to obtain those equations is that we're going to impose a requirement, and the requirement is that we're going to enforce certain values of the solution at the nodes. Okay? Right, and so if you write it out, what we're basically saying is that at node 1, we're going to have a nodal solution called u1, and at node 2, we're going to have a nodal solution value of u2. Okay, and so what we're going to do is that we're going to use this equation right here and basically just say that when x is equal to x1, Let me write out the coordinates here. And so let's say that at node 1, the coordinate is x1, and at the other end we have x2. Okay. Right. And so basically we're basically gonna apply boundary conditions on this equation, right? And so basically what we're gonna say is that when x is equal to x1, then the solution has to be u1, and when x is equal to x2, then the solution has to be u2. Okay. All right, and I'll show you what that looks like on the next page. So, but before I get there, are there any questions on this? Okay. All right, and so let's go ahead and take a look about what that looks like. All right, and so if we apply our, you can think of them as like boundary conditions. Okay. Basically, what we have is u at x1. This is going to equal to u1. Okay. And then u at x2 is going to be equal to u2. Right? Okay. And so that's our second equation, right? And so these two right here, this is a system of two equations, right? And our two unknowns are the constants. Okay. And so we can solve the system very quickly just because it's relatively simple. Okay. And so actually solving this is not, I'm not going to test you on it, so I'm just going to go really quickly. But if you want to follow along, you can look at the video back again, right? All right, and so I'm just going to subtract these two equations, and so that's going to cancel out the a zeros. Okay, and so we have u1 minus u2 is equal to a1 times x1 minus x2. Okay, and so if we divide both sides by x1 minus x2, we get a1 is equal to multi gestures. Right? So a1 is going to be equal to u1 minus u2 divided by x1 minus x2. Okay. And so we plug that back into either one of our equations. Okay, and so we get u1 is equal to a0 plus u1 minus u2 minus divided by x1 minus x2 times x1. Okay, and we get that a0 is equal to u1 minus u1 minus u2 divided by x1 minus x2 times x1. Okay. Okay. And so those are the solutions for two constants that we obtained by solving this linear system. Okay. Right. And so a lot of the theory behind a lot of the different elements that we'll see later today is that they're basically solving linear systems just like this. Okay. All right. Any questions on any of this? Okay. All right. And so you might be asking why are we using the nodal values, right? And so why are we enforcing values here at the endpoints, right? And not anywhere else. Okay? Because this u1 and u2 we actually haven't defined yet. They're kind of just the way I've kind of defined them is those are just the solution to our finite elements at the nodes of our mesh. Okay. Right. And so it's not like those are the true solutions or anything like that. Those are just kind of you can almost think of them as like kind of just at this point they're just kind of placeholders, right? But the reason that we care so much about the nodal values is that the nodes are where one element kind of borders another element. Okay. Okay. Right. And so it's really important in order for and you all have seen your meshes up to this point, right? You have thousands and thousands of elements sometimes, right? It's really important for a consistent finite element solution that when you go from one element to the next one, right? And if they share the same node, then both elements should get the same answer at the same node, right? And so one element shouldn't be saying that the answer at this node is 7, whereas the neighboring element, that says that the answer is 4 or something like that, right? Otherwise, then our method wouldn't work at all, right? And so what this does, and so by solving for the solution in terms of these nodal values, then we ensure that we have what's called a consistent finite element solution. Okay. Right. And the way that we ensure consistency is that we formulate the solution on each of the elements in terms of its nodal values, okay? And we keep those consistent throughout this entire process, right? And so as long as we kind of assume from the start that each of the different elements, where they're bordering each other, they share basically the same solution value there, then that ensures that we have this consistency requirement satisfied. Okay. All right. All right, so that's a little bit of a deeper look into what's going on with the element order and kind of why why the cost goes up when you choose quadratic. Okay, because for a quadratic element, you can see here that we have 2 nodes in this element from linear, but for a quadratic element, you're going to have actually 3 nodes. Okay? And so you have node 1, node 2, and actually the node that's in the middle, that's actually given the higher number, so that's node 3. Okay. And so for quadratic elements, and you'll see this for 2D and 3D as well, that additional nodes are placed kind of in the middle of the element, usually at the middle of an edge, right? Basically where it can be shared with the neighboring element. Okay. Okay. And so before I jump into 2D element types, I do want to talk a little bit about what shape functions are, because you'll probably hear that term, one way or the other if you continue to study finite elements. So I want to make sure that you guys are aware of that. Okay. All right. And so shape functions, you can kind of think of shape functions as kind of a convenient manifestation of the element order and the nodal solutions. Okay. Okay. Because what shape functions do is that it allows you to formulate the approximating function in terms of the nodal values. Okay. Because we've already seen with a 1D 1D linear polynomial, right? We've already seen that we can formulate in terms of A0 and A1, right? So we can say that U of X is equal to, actually let me just go ahead and write it all in. Okay. And so A0 is U1 minus U1 minus U2 divided by, I think X1 minus X2, right? And X1 minus X2 times x1 times x. Oh, no, sorry. Minus x1. So that's a0 plus a1. A1 is u1 minus u2 divided by x1 minus x2. Okay. And so that's one way that we can formulate this this finite element approximating function. Okay. Okay. But another way, and so if we take this function here and we kind of rearrange it algebraically, we can put it into a form that's a little bit more convenient. Okay. And I'm going to be doing this from memory. And so let's see how well I do this. Okay. And so one way that we can do it is we can say that there's one term times u1. Okay. And this is going to be equal to x minus x2 divided by x1 minus x2. Okay. No, that x over there is just regular x, and so that's not x2. Yeah, because this coefficient here is a1, and so that's the coefficient in front of x. Okay. And so I did this from memory, and so this looks right to me, but I'd have to go double check this. But if you rearrange the the first boxed expression and you kind of work the terms around, you should get something you should get exactly what's in the bottom. Okay. All right. And so what's the significance of this, right? And so why do we even rearrange this? And so you can see here, this first term, this is the only term with u1. Okay. Right. Whereas the second term right here, this is the only expression with u2, okay? And so we basically rearranged our finite element polynomial such that it's broken up into one of the terms that's associated with node 1 and another term that's associated with node 2, okay? So this is u1 node 1 okay? And u2 node 2. Right, and so basically, we've broken up our polynomial such that we have very clear that this term here is associated with node 1 because it has a u1 in front, whereas the other term is associated with node 2 because it has a node 2 in front. Okay. Right, and so what I'm boxing here in blue, these are known as the shape functions. Okay. And so the way to think about shape functions is that there's there's going to be one shape function for every node in your mesh, okay, or in your element. I'm sorry, okay. And so there's one shape function per node, okay. And there's also the polynomial order of these shape functions matches the polynomial order of your element, right? Because if you look at the function that I've boxed in blue and you kind of took that, if you took that as a standalone polynomial, you'll see that that is a linear function. So just like our linear element, right? And so same thing with the second box one, right? And so if you look at the second box function, and just noting that x1 and x2, those are both just constants because those are just locations of the nodes. You'll see that that also is a linear function, okay? Right. And so I'll write down what I want you guys to remember for shape functions on the next page because it's going to help our discussion of the different element types. Okay. Okay. So any questions on this? Okay. All right. So shape functions. And so the first characteristic of shape functions is that you're going to have one per node. Okay. Right, and so if you look at the type of element that you have and you count the number of nodes that are there, you know that you're going to have one shape function associated with each of those nodes. Okay. And then the other thing about shape functions is that their polynomial order, it has to match the order of your element. Okay. All right. And so, that's all that I really want to dive into shape functions. And so, if we were to go deeper into the theory, shape functions would kind of form the basis of our analysis. But, I just wanted you to kind of be aware of what they are and how to think about them. Especially going forward, because, from here, we're going to go through all the different 2D and 3D element types, both of the shapes and both of the orders. And so, this kind of discussion here kind of sets the pretext for that, just so that, we're all kind of on the same page. Okay. All right. Any questions on shape functions or element order? Okay. All right, so let's start going through the different element types. And so let's start with 2D, just because those are a little bit simpler to do. Okay. All right, and so, if you think back to our discussion on meshing basics, you know that we have basically two options for 2D elements, right? And so we can either go with the quadrilateral, okay, or the triangle. And a quadrilateral is a 4-noded shape, okay? And a triangle, of course, is a 3-sided shape, okay? And both of these elements here, both of these shapes have a linear version and a quadratic version, okay? And so we're going to go through each and every single one. And so we're going to talk about what the approximating polynomial looks like, what the shape functions look like, okay? And how they solve for each of them, okay? All right, and so let's start with the quadrilateral, because that's it's a little bit more balanced than the triangle one, okay? And so let's start with the linear quadrilateral. All right, and so linear quadrilateral looks exactly as you see above, okay? And so there's going to be 4 nodes. And actually, I think the notation I use in the notes is I use letters. And so this is going to be node I, node J, okay? This is going to be node M, and this is node N right here, okay? And then each of these nodes have their respective coordinates, okay? And so the coordinates for node I are going to be xi, yi, okay? The coordinates for node J are going to be xj, yj, okay? The coordinates for node M are going to be xm, ym. And then the coordinates for node N are going to be xn, yn. Okay. All right. And so that's kind of the bare minimum that you need to define a quadrilateral, because it needs to have 4 sides. In order to have 4 sides, we have 4 nodes. Okay? And so what that tells us is that because there are 4 nodes, there's going to be 4 shape functions. Okay, and because it's a linear element, then our shape functions, they're all going to be linear, and our interpolating polynomial is also going to be linear. Okay. All right. Any questions on any of this before we start going over the functions? Yeah.
So if you have a mesh that's made of linear quadrilateral elements, do you know for a fact that the amount of nodes you have will always be 4n, where n is a number of levels?
It's going to be less than that because each element is going to share nodes with its neighbor.
Okay.
Yeah. And so, the exact ratio is going to depend on the geometry because sometimes, if you have, one node might be shared by anywhere between, 2 elements or 3 or 4. It depends on that.
Gotcha.
Yeah. Okay. All right. And so let's go ahead and start to look at what the interpolating polynomial looks like, or the finite element polynomial. Okay. And so first of all, we know that it's a linear function because we have a linear element, okay? And because we have four nodes, we know that we're going to have 4 unknowns in this function as well, okay? All right, and so unfortunately, my notes, I changed notation here, and so it's not U anymore, so it's T, okay? Right, and so I think when I wrote these notes, I was under I was actually teaching heat transfer for the first time when I made these notes, and so that's why these are T, okay? All right, and so our function here, which is a function of x and y, because we're in 2D space, okay? Right, and so we're going to have 4 constants here, or 4 terms, okay? And so first we have our constant term, and so that stays the same, okay? Then we have our linear term in x, which is going to be a1x, okay? Then we have our linear term in y, which is a2y. Okay. Okay. We need one more term, but we're actually all out of linear terms, okay? Because we've used x, we've used y. And so the last term there is actually a cross term, okay? And so the cross term is going to be xy. Right? And so a lot of people look at this and they see that, hey, that's not a linear term. This is a quadratic term because you're multiplying 2 things next to each other. Right? And so technically, you're right. Technically, this is a quadratic term because you have two independent variables multiplying each other. Okay. But what we call this in finite elements, that we call this the pseudo linear term. Okay. Okay. Because technically, yes, you multiply x and y, it's technically a quadratic term, but at the same time, it's linear in x and it's linear in y, and so it's pseudo linear. And so, just to kind of respect the linearity of this, we call that pseudo linear, even though technically it's not. But in order to actually have a consistent solution with the quadrilateral, we need that extra term there in order to have that 4th constant. Okay. And so just like we did with the 1D linear case, in order to solve for these constants, what we're going to require is that we're going to require that the solutions match the nodal values. Okay. Okay. And so we're going to have 4 equations and 4 unknowns here. Okay. All right. I'm not going to make you solve that on paper because I don't want to do it. And I know if I don't want to do it, then I know you guys don't want to do it. And so, we're just going to skip right to the solution. Okay. But we're going to skip to the solution. But before we do that, we're going to form this rectangle in a kind of an interesting way. Okay. Because it makes the formulation of the shape functions a lot more convenient. Okay? And so before we jump to the solution, I'm going to introduce something called the natural coordinates. Okay? And this basically places restrictions on what the coordinates of the nodes of this rectangle are going to be. Okay? Because if you looked at our rectangle on the previous page, you know, I kind of just drew a rectangle in kind of free space where all the x and y coordinates can basically be whatever they want. And so here I kind of drew them such that, you know, they're all the sides are parallel to each other, and we have two horizontal lines and two vertical lines. But you know, we're not restricted to this, and so we can have like a what's called a trapezoid, or we can have, you know, I think it's called a rhombus, right? And so you can do, you know, kind of, you can put these nodes anywhere you want. But the thing is, you know, if you have kind of generic x and y coordinates like that, it makes your algebra really, really messy. And so what's typically done for these, you know, for 2D and 3D elements, when things start to get messy, is that they map everything onto what's called the natural coordinates. And so for a quadrilateral, it looks something like this. And so here is the origin, and so that's going to be 0, 0. Okay. And then the rectangle is drawn around the origin. Oops. Right. And it's drawn around the origin in a way that the coordinates of this upper right corner right here, this is going to be 1, 1. Okay. The coordinates in the bottom right one, this is going to be 1, -1. Okay. And the bottom left, we have -1, -1. Okay. And in the top left one, we have -1, 1. And so if we have these coordinates in our rectangle, it makes our algebra a lot simpler. It makes our lives a lot easier. Okay. But you know, because you know, we're not, you know, we say that this is kind of an imaginary rectangle. It's not actually in physical space. Because in physical space, you know, your rectangles or your quadrilaterals can have any kinds of coordinates that they want, right? And so they can be any kind of x and y, just like we talked about. But because what we're basically doing is we're mapping from the physical coordinates onto these natural coordinates, we have to give the coordinate axes a different name. And so instead of x and y, we're going to have xi. I think that's a xi anyway. I'm never sure because all the finite element professors that I've had really heavy accents, and so I could never really tell what they're saying. And so I always assumed that this was called a xi, but I also sometimes call it tornado because it looks like a tornado. Right? And then the other coordinate is called eta. And so this one I do know. So this one I know that this is called eta. But you know, pretty sure the other one is called xi. Right? That's what I've been calling it all these years, and that's what I'm going to stick with. All right. And so, you know, with these natural coordinates, and you know, you'll see me use this throughout the rest of this week, that, you know, these are not physical coordinates, and so that's why we don't call them x and y, but they're a convenient coordinate system to help us formulate the shape functions in a convenient way. Okay, but the way that these actually work in practice is that, you know, you can take these shape functions and these natural coordinates, and you can map them onto any physical coordinate or physical element, and so that'll give you a consistent solution. Okay, but we use these natural coordinates just because they're a lot more convenient for formulating the shape functions. Okay. All right, any questions on this before I write out the shape functions for the linear rectangle? Okay, all right, and so let's see, 2 more minutes. Okay, let me write down these shape functions, and then we'll probably call it a day after that. Right. And so remember, we have one shape function per node, and so this is going to be the shape function for node I. And so remember, that was the one in the bottom right. Okay, and so it's going to be 1/4 times 1 minus xi minus 1 minus eta. Okay. Okay. Then we have Sj. Sj is 1/4 1 plus xi times 1 minus eta. Okay. Sm is 1/4 1 plus xi 1 plus eta. Okay. And Sn is 1/4 1 minus xi and 1 plus eta. Okay. And so those are the shape functions that are associated with each of the nodes in our linear quadrilateral. Okay. All right. And so before we wrap up today, basically how Wednesday is going to go is that we're just going to go through a rapid fire round of all the different element types. And so we'll go through the quadratic quadrilateral, the linear triangle, the quadratic triangle, and then we're going to go to the 3D one. So linear tet, quadratic tet, linear hex, quadratic hex. Okay. And so what I want you guys to pay attention to is, first of all, what the order of the shape function looks like compared to the order of the element, and how many shape functions do we have compared to how many nodes there are in the element. Or in other words, how many nodes do we need in the element in order to have this order for that particular element. Okay. All right. Any final questions before we wrap up for today? Okay. All right. So thank you guys for coming today. I know it was kind of a lot of abstract math, but hopefully that kind of sets the stage for where we're going with that, right? And so enjoy the rest of your evening. Thank you guys for coming out, and I'll see you guys on Wednesday.
For the next project, you suggest we go back to
I think that would be the best because a lot of the report is going to be like how do you use a meshing for these evaluations, and I think until you get results that you're happy with, I think you're going to be tinkering with those a lot. And so if you write those sections of the report first and you find out it doesn't work, then you have to go back and rewrite the report. So I would say finish the simulations first and then go back. Thanks, Jacob.
and for the meshing, if I try something that I work, should I mention them the
Yeah, actually, I think that'd be good. And so, yeah, I always do appreciate reading that. Just like, what did you learn from the situation and what didn't work? Because that's important learning too. And so if you tried something that didn't work out that well, you can talk about that too.
Sure. Thank you.
Yeah.
Hey, Professor.
Hey.
I'm Tristan, by the way.
Oh, hey.
I was just gonna say it was funny that you're talking about the scatter plots and the fitted curves. 'Cause
Yeah.
at work, I've been collecting a bunch of pressure drop data lately.
Mhm.
I'm developing curves for flow rates.
Nice.
Flow rates versus pressure drops.
Yeah.
So I've been using that a ton. And I'm always looking for the I-squared value to get as close to 1 as
Oh,
possible.
yeah. Yeah.
I got one the other day that's 0.9996. So I was
Nice.
like, wow, that's a really good R-squared value.
Nice. Yeah, that's pretty good.
I just thought it was a funny story.
Yeah. No, it's used a lot. I mean, just approximating just polynomials in general. Like I remember learning least squares when I was in taking math class as an undergrad, but then there's all the finite element stuff which I became familiar with in grad school. But yeah, just fitting functions to stuff is super useful.
Oh, yeah.
For so many different things.
Definitely. All right. Have a good one.
Thanks, you too. Hey, yeah, I'm glad you came back.